Okay, so for exam 2 part 1, our objective for part 1 is to basically define functions in order to calculate head drop and the flow rate in a single pipe segment. And we're going to use the nodes from which the water flows and from the given lengths of pipes. So the first step to our code is going to be to import numpy as np. And we're going to go from there from scipy dot optimize, and then import our Newton root for our Newton solving method. Alright, let's go ahead and run that, and then add a code. Alright, so our first function we're going to define is our FF, fanning friction, and what we're going to need for that is our Reynolds number and our roughness, which we're going to call ED for epsilon over the diameter. And then from there, we're going to go ahead and define our A as this 2.457 times our np.log of 1 over our 7 times our Reynolds number, and then that's going to be taken to the 0.9 power plus 0.27 times the roughness, and then that all is going to be taken to the 16th power. Alright, we got A. Now let's go ahead and define B. Our B is going to be 37,530. So that divided by our Reynolds number, also taken to the 16th power. Okay, and finally we're going to go ahead and return our 8 times our 8 divided by our Reynolds number taken to the 12th power, and we're going to add our defined variables a plus b, and then take that to the negative 1.5, and then take that to the 1/12. Okay, let's run that, make sure everything's right. Alright, we have a function, invalid syntax, line 1. Oh, I think I'm just missing a colon. Let's see this one. Perfect. Alright, cool. Alright, let's add the next code. Now we're going to go ahead and define our set of variables. So we have pi. That is going to be equal to our np.pi. With that. Cool. Alright. We're going to say G is going to be equal to 9.81 for our acceleration due to gravity. Our rho is set to 1,000. Our mu is going to be equal to 0.001, and our roughness is going to be also 0.00. Cool. Alright, everything's good. Next, we're going to define our next function, and that function is going to be our delta head. Alright, yeah, our delta head. So we're going to define d head. That's what we're going to call it. And the variables are going to be q, l, k, d, and our roughness, ed. I can forget the colon this time. Alright. Then we're going to have our v is going to be set to np absolute value for q over pi times d to the 2 divided by 4. Alright, now we're going to set our Reynolds number. It's going to be equal to rho times V times D. Ooh, bless me. Thank you. Divided by mu. And we're going to return our negative NP dot sine Q. Multiply that by our K plus 4 to the frictional factor F of Reynolds number, and then the roughness. Multiply that by the length over the diameter, and multiply V to the second power over 2 times acceleration due to gravity. Alright, we have that. We're going to make sure that's right. Okay, line 4, we are missing something. Oh, put an equal sign there. Whoops. Alright. Cool. Alright, next line. We're going to go ahead and define our next function, which will be our flow. That will be using the variables delta head, L, K, D, and ED. Alright, now we have absolute. Our delta head is going to be set to NP dot absolute, and then variable delta head. Okay, and then you're going to have an if statement. If the absolute delta head is equal to our P dot absolute. Oh, sorry. Not equal to, is less than. If it's less than 1 times 10 to the negative 10th, so 1 e negative 10, then we're going to return 0. And we're going to have Q underscore G is going to be equal to our pi times our diameter raised to the second power over 4 times our NP. Okay. Let's go ahead and run that. Looks good. Alright, next line. Actually, we're going to go ahead and continue on this line. And define our next one, which is going to be our F underscore 0. Of Q. If we find that, we're going to return delta D head for the variables Q, length, our K constant, the diameter, and roughness. And then we're going to subtract our absolute delta head. Okay, almost done. I think all that's left to do is to set our RES. We're going to set equal to Newton F underscore 0 q underscore g. This is going to be using the Newton solving method referred to at the beginning, and then we're going to return on np.sign delta head times res that we just defined. Let's go ahead and run that, make sure everything's good. Alright, everything's good to go. So that is the code for part 1, which is basically just defining our functions that we're going to use to calculate the head drop and flow rate in that single pipe segment.